Today we have Brian Young, and I don't know if you remember him. I think you gave us a talk about a year ago also in the FEM workshop.
Yes.
So we're very happy to have you here. Brian is an expert in electromagnetics and digital signal integrity and antenna design, among others. Now I believe you're retired, right? But you worked in many places.
Yeah.
So
I work full time now. I just don't get paid.
yes. Okay, and today you're gonna talk about a full wave electromagnetic simulator for frequency domain S parameter calculations. Okay, we're very happy to have you here. Take it away.
Okay, thank you. So I have a kind of a standard agenda. Go through the motivation for this work, features, S parameters, a little bit of background there. Then the construction of the 3D simulator, how I've implemented adaptive mesh refinement, and then a number of examples in discussion, a few comments on a regression suite, and a conclusion. So the motivation for this work is that I'm not aware of any low cost or free frequency domain S parameter electromagnetic simulator, and because of that, there's very limited ability for an individual to explore ideas at home or to work on continuing education. So the target audience is basically anyone who would like to be able to do 3D electromagnetic simulators and produce S parameters to try to come up with new things or self-educate, or even say small startups that can't afford the very high cost of the commercial simulators. So as far as feasibility goes, I'm a one-person effort, so you have to leverage existing open source projects. So to produce a 3D electromagnetic simulator, here's what I'm doing. I'm using FreeCAD for the CAD, GMesh for meshing, FEM for the finite element, and then visualization with ParaView. And that's essentially a simulator right there. So all you need to do is just glue it all together, which is quite a bit of work, but not nearly as much, I think, as putting together any of the pieces that are required to pull together a full-scale simulator. So the features I'm targeting is a full wave time harmonic 3D electromagnetic simulator that computes the electric and magnetic fields, and then from those fields extract S parameters between 2D ports on the surface of the 3D space. Courtesy of FEM, it supports arbitrary higher order elements. Courtesy of FEM, PET-C, SLEP-C, and some custom code, also parallel processing via MPI. And then I'm also leveraging FEM's adaptive mesh ability to do adaptive mesh refinement. So so far, the one added feature that I need to add, one feature I need to add before releasing it is to add the impedance boundary condition, which I just left off because I didn't want to mess with it to start off with, because there's so many things that have to be pulled together to get it started. So S parameters, in case you're not familiar with them, that's short for scattering parameters. It links the incident and reflected waves at the ports of a 3D volume. And for my experience in engineering across a number of companies and technical fields, is S parameters just dominate. Frequency domain S parameters. That's just what's used to bring electromagnetic simulations into circuit simulations and for performance analyses. So for a practical simulator, in my opinion, that's just a must-have requirement. So that's why the focus on this electromagnetic simulator is the primary output is targeting S parameters. Okay, so a quick background, one slide background on S parameters. If you have a 3D black box with N ports, at each port you'll have an incident wave, and then some fraction of that wave will bounce back, or some energy will come out from energy driven into another port. So the convention in S parameters is the incident wave is A, the reflected wave is B. If you have N ports, then you can relate the outputs to the inputs via the S parameter matrix. So the target action then analysis is to get the 3D solution so that you can drive it with drive the space with incident waves, get the reflected waves, and then produce the S parameter matrix, which is the output. So the basic process is define the ports, which would be 2D flat surfaces on a 3D space. They have to be flat because the assumption is that the energy coming into the 3D space is from a transmission line or waveguide, meaning that there's no dependence. The only dependence in the field is in the z direction, so it has to be flat. Solve one column at a time by driving port I, and then if you terminate all the other ports, then the reflected energy, or all the for I not equal to the driven port, then those are zero because there's no energy coming in. So you can drive port I, get all the energy coming out of the other ports, and then you can pick off the S parameter matrix one column at a time. So you have to repeat the simulation n times to fill out the full matrix. Once you've done that, you can then output the results in a touchstone file format, which is what all the circuit simulators pull in. Results viewers, plotters, everything depends on on touchstone files. Okay, so this is a little bit more about the setup. Suppose you have a 3D space. You define the 2D ports on at each place where you want to drive energy and take energy out. The simulator uses FEM's par submesh functionality to extract the 2D meshes on each of the 2D meshes at each port. The electromagnetic simulation, it's solved for the 2D simulation, assuming it's a transmission line, using OpenPAR-EM2D, which is what I presented at the workshop 2 workshops ago. Then the 2D field solution is applied to the 3D space, which forces the fields to take the 2D field solution, and then an absorbing boundary condition is applied to the other ports. So that gives you a unique setup that you can then solve the 3D electromagnetic simulation. And then you just cycle through and repeat that for all the ports. And when you're done, you can extract the S parameters. So moving on to the 3D finite element setup, the simulator uses the weak form of the wave equation. So this is basically exactly what everybody else does. So there's nothing innovative here. And FEM is very well set up to solve this equation with the one exception I'll talk about, which makes it a little more interesting. So the first term can be solved with the curl-curl integrator, second term with the vector FE mass integrator. The third term is the surface term, and that's where you need to apply boundary conditions, and that's where the ports are. So you have to bring in the ports from the surface term. So the surface term can be broken into the end ports and then everything else. The surface that's not ports right now can be a perfect electric conductor, which is easy to apply directly in the matrix by manipulating the DOFs. And then there's the end ports, which have to be considered. So copying the port setup, the surface for the ports. There's the part with the DOF manipulation, and then there's the part that has the n-cross curl of E, and that term is not directly supported in FEM. So that's where a little bit more work has to be applied to solve what needs to be solved using FEM. And the way I'm handling that is very similar to what's done in the literature, where you apply a vector identity to break the electric field into the tangential and normal components. And then to the derivative term, because you're making the assumption that the field at the ports is coming from a transmission line, the derivative with respect to the direction you're traveling is known because it's just the propagation constant. So that's just written out of here on the right, where the derivative, because of the known dependence in the direction of propagation, is e to the minus gamma n. You can take the derivative, and so you have one term out of this is just gamma times the tangential electric field, and that can be implemented with a vector FE mass integrator. So that term is easy to take care of. The next term is a gradient term of the normal component. And that operation is not supported in FEM for Nedelec elements because it includes a normal component on the boundary, but Nedelec elements don't have the normals on the boundaries. So what I'm choosing to do is to just neglect this term. And I have a whole slide next to talk about what happens when you neglect this term. So from a physics point of view, zero gradient of a non-zero normal component is not physically realizable. So effectively, that just means I'm assuming that the normal component of the electric field is zero. From a transmission line point of view, what that means is that only transverse electric or transverse electromagnetic transmission line modes are directly supported, so not TM. From an engineering point of view, the TE and TM cases dominate what everybody looks at. I'm not sure I've ever seen anybody use anything but a TE or TEM, because these are the kind of practical transmission lines used in real applications like microstrip, strip line, coax, triax, slot line, coplanar waveguide, rectangular waveguide, and generally any end conductor transmission line. So in practice, the TE restriction is not significantly limiting. So I'm not expecting this to be a problem. Now, if you try to solve with a non-TE mode or use a TM mode, it will happily solve it, but you will get a bad answer. It distorts the field, so you'll get the wrong answer. But if you really, with the way the simulator is currently set up, if you really wanted to get the S parameters for TM modes, what you could do is set it up like you would an experiment in the lab, where you launch TE modes, then include in your 3D space transitions to the TM mode of interest, and then you could do a standard de-embedding operation. So not very convenient, but if you really do need to do TM modes, you could actually do it that way, kind of the hard way. A lot of times, the fields of interest, the modes of interest, are quasi-TEM, TE, or quasi-TEM modes, where EN, the normal component, is small compared to the transverse component. It's usually very small. So there will be a small error there. I'm not expecting that there would be a significant hit to accuracy. So for engineering purposes, I think that quasi-TEM, quasi-TM modes, that it'll just be fine. Eventually, I'd like to relax this restriction. One would be by including the gradient term somehow. That would either my understanding of FEM would have to greatly increase to implement that myself, or it need to be added by the FEM team. Or I could implement a perfectly matched layer boundary condition to completely absorb reflections, so that the distortion caused by the field at the TM field at the ports would not occur. Okay, so top level implementation details. starting at start here, the starting point is a 3D par mesh, so import a mesh into a par mesh, then go through the bilinear forms according to sort of standard methodology, very similar to the examples. The difference is, since I'm doing frequency domain, I need to use complex numbers. So there's a real and imaginary version. I'm doing matrix operations on a CPU. So I go to two hyperpar matrices to get the real and the imaginary part. But I need to solve them in complex. So those are converted to complex PETSI using a conversion routine that I wrote. Could not find one that would do that. That seems to be pretty effective. Then on the 3D par mesh, you can use the par submesh methods in FEM to pull off the meshes for the 2D ports. Those can then be exported and solved in OpenPAR EM2D. And then the fields are brought back into the 3D program to do the custom system integration. So it's a custom construction because it's complex, but also I'm applying DOFs from the ports and applying PEC boundary conditions to form a complex linear system, which is then solved in PETSI. And then once that's solved, then you can pull out the real and imaginary parts of the electric field. Similar flow as for the electric field, solve for the magnetic field. And then once you have the E and H, you can then post-process to solve for S parameters or export for viewing and pair view. So after you have the 3D electromagnetic solution and you want to go to the S parameters, there is one issue that has to be addressed, and that is that at the driving port, you have set it up to drive the energy into the problem. Well, there's reflected energy coming out of the problem. So there's an electric field wave traveling into the space. There's electric field wave coming out of the space, and you have to separate those two because, for example, reflection is the output divided by the input. So you have to separate the total E into its forward and reverse traveling components. And to do that, at least the way I'm doing it, is you need the magnetic field to separate the two. To simplify things in this operation, I'm only using the tangential components because in all practical applications that I'm aware of, the tangential components dominate the longitudinal components at the ports. So there's no need to mess with the normal components. So the setup for that is you have the total field at port I is going to be a weighted sum of the field traveling in the plus direction and field traveling in the minus direction. So the key is to find those two weights. One way to do it, which I'm finding to be very effective, is to dot product the fields with the dot product with the field in the minus direction, integrate over the surface of the port, and those inner products are easily implemented in FEM. Then replace the field in the minus direction with the field in the plus direction, and you end up with a relatively simple equation where you have one equation and two unknowns. You know E0 and you know E2 from the inner products, and now you're still looking to find C1 and C2. Then repeat the operation for the magnetic field, and what you and this is where the trick happens, is when you replace the magnetic field with the negative component with the positive component, there's a sign change. So you work through the inner products and you end up with another equation, but now there's a minus sign in the equation, so that allows you to uniquely solve for the weights, splitting the positive and the negative directions of the waves. So with those weights, you can then move on to solving for the reflection coefficient at the driving port. So in S parameters, they're always talked about terms of A's and B's. A's towards the 3D space, B's are the reflected. You can talk about those in terms of voltage waves or current waves. Right now, I'm implementing it as voltage waves. So A sub I is the voltage wave traveling in the plus direction divided by the characteristic unit of the port, and B sub I is the reflected wave divided by the characteristic impedance of the port. So those voltage waves amplitudes are proportional to the weights. So you can substitute in the weights and then simply divide it out. So the reflection coefficient, SII, is B sub I over A sub I, and then you can calculate that with the known weights from the all the inner product calculations. Now for the off-diagonal terms, SJI, there you can just use direct calculation with voltages using the definition that SJI is B sub J over A sub I. So you have the voltage wave at port J divided by the voltage wave at port I, and you can just for at port J, there is no incident wave, so the total voltage is just the voltage traveling away from the space. So a direct calculation of the voltage gets you V sub J. On V sub I, that's at the driving port. There you need the voltage traveling towards the space, not the total voltage, but we have the weight for that. So we can calculate the total voltage, apply the weight for the portion that's going towards the space, and we can get the needed voltage component traveling towards the space. So then dividing that out, we get the equation to calculate the off-diagonal S parameter terms from the 3D field and the weight and the weights. Okay, so with the 3D solution and the S parameters that in effect completes the electromagnetic simulator, the next step is to implement adaptive mesh refinement. And for that, I'm following the setup used in the FEM Tesla mini app, where the errors are calculated using the curl integrator on E, the RT elements for flux and ND elements for the smooth flux. The difference that need to be implemented here is that there's real and imaginary electric field components. So the error has to be calculated for both real and imaginary parts and then combined. Then, because as refining the mesh, you'd like at each iteration to refine the mesh that overall improves the S parameters. So the errors need to be calculated as you drive each port and then saved. And then you can combine the errors from all of the ports, from all the driven ports, and then threshold that total number of ports to find elements to refine. So that way you're refining elements in the areas that affect the overall S parameters. Eventually, it just uses the PAR-MESH general refinement, so it gets back to sort of the standard methodology at that point. Then to test for convergence, since the primary output is the S parameters, the convergence test is on the S parameter matrix S. So for that, I'm calculating an error of taking the error at the S parameter at the nth iteration minus the S parameter at the n minus 1 iteration, and then multiplying by the inverse of the S parameter at the nth iteration. So more or less just a kind of a standard error calculation, and then take the max column norm of that calculation. So you can iterate until the error drops below some sort of a user-defined limit. Then there are options you can apply to that, like do you meet a prescribed error limit once, or do you meet it 2 or 3 times in a row? You can also there's also the option to apply adaptive mesh refinement at multiple frequencies if you want to straddle a resonance or something like that. One thing I'm seeing, which may or may not be an issue, it's not hurting me right now, but as I'm applying adaptive mesh refinement with the FEM library, at each iteration, the mesh quality goes down a little bit, especially at the ports. That's not causing me numerical issues in any of my examples so far, but it'd be nice if the quality of the mesh somehow magically stayed constant as adaptive mesh refinement was applied. This may be a mistake on my point, so if someone knows that this isn't right, I'd love to hear from you. Okay, so I'd like to go through some examples. So this first example is a pretty strenuous test of the quality of the solution, where you take a rectangular waveguide that's filled with that's dielectrically loaded, and with a perfect solution, the reflection coefficient S11 in dB goes to minus infinity. If there's any imperfection in the space, then you'll reflect energy off of any imperfection at the mesh or anything, and then S11 will not be minus infinity. Because it goes to minus infinity, you can push it as hard as you want to look for issues. So in this example, the mesh is very coarse, starts off at almost a wavelength. So if you're using linear elements, there's no way you'll get a good answer. So the plot on the lower left shows a p-convergence as the finite element order increases. So the reflection coefficient is the blue curve. At first order mesh elements, the reflection coefficient is near zero. So that's an extremely poor answer. But as you increase the order, the error, the S11 regularly improves until eventually it hits what appears perhaps to be a noise floor of around little, I guess that's like a minus 170 dB or something. To my experience using commercial simulators, that's a very good result. Then for the phase error, the delay through the section, it starts off once again with a very high error. Around the fifth or sixth order elements, the error is starting to be very good, and it continues to improve as the order of the finite element solution increases. The plot on the right just shows some metrics to check the quality, where there is the reciprocity error, which is S12 has to equal S21. If you have a low quality solution, they won't be equal. So the magnitude of the reciprocity error comparing driving one port versus the other steadily improves as the finite element order increases. So that's a good result. The phase reciprocity error also continues to improve until some sort of noise floor is hit. So that's very good. There's no losses in this problem. So that means that S11 squared plus S21 squared has to equal 1. So you can calculate an error based on non-physical energy loss. And you can see that the passivity error with finite element order continues to improve to a very small number. So in this example, this is showing that it's possible to get very, very, very good electromagnetic results to very low errors. Now, this is a matrix solution on a CPU. So you get what you would expect, where as the finite element order increases, the runtime goes up at a very quick rate. This is applying, same example, applying adaptive mesh refinement instead of P refinement, that's H refinement, to check to see if the adaptive mesh refinement is working well. And in general, you can see at all the curves as with each iteration, the answer steadily improves and you get less error. So I won't go into detail in these, but it's showing the expected response of fairly linear improvement in the answer as you as adaptive mesh refinement continues to refine the mesh. The plot on the lower left is interesting for me, is that if you look at the phase error of the delay through the problem, if you just pick any error level, say minus 40 dB and slide to the right, what you find is that you get the I need to be on the plot on the lower right, sorry. But same concept. Go pick a line, go across, and what you find is that to beat the expected error, you always end up reaching that error in the lowest runtime with a higher order element. The problem is you don't know exactly what order element that would be required, but from these results, what I find in general is that within reason on runtime, you're better off using as high order element as you can get away with, along with adaptive refinement. And that will ultimately end up with the best answer at the lowest runtime. Of course, that's problem dependent, so it's kind of a feel your way through it on any given problem. Okay, so here's an example with a WR75 waveguide with a dielectric puck in the middle of it. And this is solved twice, once second order with AMR, once is fourth order with no AMR. And this is the published result. The red and black lines are OpenPAR-EM 3D, and then dots and crosses are the published results. And you can see that the result is very good, and that the using adaptive mesh refinement or no adaptive mesh refinement with sufficient order can basically get you the same answer. Here's a WR75 waveguide T-junction. This is solved with no adaptive refinement. And then comparing the results against the literature, once again, there's very good results. In this particular example, the mesh, the maximum edge length is a quarter wavelength, and with fourth order elements, quarter wavelength mesh is no issue. This is a more complex example from the literature where there is a microstrip line on gallium arsenide with, leading to another microstrip line on gallium arsenide with a gap, a bridge, and the block of material with the bridge is variable, has a variable dielectric constant. This is solved with fifth order elements with no adaptive refinement and across four different dielectric fillings. The agreement between measurement and between this simulation and the published result is very good. This is a slot line step. Slot line is generally very challenging for electromagnetic simulators because it's an edge coupled device, and edges have strongly varying electromagnetic fields near the edge. So you need a lot of refinement right next to the edge. This slot line step is solved half of it using symmetry. This using third order finite elements with 11 passes of adaptive mesh refinement with a very tight convergence requirement, 0.001. And the agreement between these results and the literature are once again very good. There's a little plot on the to the right, repetitively solving with adaptive mesh refinement in one frequency versus the number of slots on my dual processor Xeon, and then fitting it on a log-log plot. The exponent is 0.655. So the efficiency for this problem is 0.655. As far as I can tell from the literature, for a memory-intensive application, that is a typical type number. If anyone is aware that this 0.655 is a very poor number, I would love to hear from you. This is the most practical engineering example I've run so far. It's a microstrip filter. It includes dielectric losses only because I haven't put conductor losses in. Using second order elements with adaptive mesh refinement with 9 iterations and a 0.02 convergence criteria. This is measurement versus the simulation versus the published measurement. So it's a measurement versus simulation. And I think the agreement is very good given the lack of conductor losses, which wouldn't be great at this relatively low frequency, but it should still have an effect of rounding off the lossless result. This problem is really challenging for a finite element, once again, because it's edge coupled. In the filter, there's the 3 microstrip lines very close together. So you have very fine meshes. You need very fine meshes in that gap, and to resolve the fields accurately. On my computer, I really wasn't able to use more than second order elements, just because it's not a very stout computer, but it still solves this well with second order elements. And then here's a sample field plot from ParaView. Since I'm targeting a general release, not just a research type program, it needs commercial type support to verify that the tool is working well. So I've put together regression suites for both OpenPAR-EM 2D and 3D. It's fully automated to run and to check for errors. It runs with and without adaptive mesh refinement. For the OpenPAR-EM 2D, so far I have 27 test cases in it, total of 43,000 checks, individual checks to verify that it's operating well. For the 3D simulator, I'm up to 17 test cases covering a variety of port types. And in addition, there are variations of taking the same problem, rotating it in space in various orientations to make sure that the ports are correctly handled with respect to positive and negative directions on importing the fields and propagation constants, so on. And so far, there's a total of 390 checks of S parameters in these test cases. So in conclusion, I presented an effective 3D full wave time harmonic EM simulator for calculating S parameters. And I think that I've well demonstrated that it produces high accuracy. A technical issue with the implementation is neglecting the gradient term, where if you want to drive the 3D space with non-TE modes, you have to do de-embedding. I do believe that that should be very rare. But if you really do need to do it, you can still go the manual route and do the de-embedding. Not having the gradient term included means that to separate the forward and reverse traveling waves, I have to calculate the magnetic field. In the literature, where they're using completely no libraries, completely hand-implemented finite element codes, they are able to implement the gradient term, and they're able to de-embed the forward and reverse traveling waves without having to calculate the magnetic field. But other than the 2x runtime hit, there's no issue. So the things left to do on the simulator are to add the impedance boundary condition to support conductor losses in antennas. It's already including dielectric losses, so it's just conductor losses. I don't think that'll be hard from an electromagnetic point of view. It'll primarily be just making sure that capturing the 3D boundary conditions and making sure that they are properly applied to the 2D problems when it's exported to solve in the 2D simulator. I'd like to add a perfectly matched layer absorbing boundary condition at the ports that would allow me to relax the TM restriction, and then write documentation and release it. And it's will be a free open source simulator. And finally, I'd like to thank Mark Stoll for many very, very helpful email exchanges that got me over the hump a few times. Okay, well, that's it. Thank you for your attention.
Thank you, Brian. That was a very nice talk.
Thank you.
Okay. Any questions from the audience? Okay, I do have a couple.
Does your what probably I
Yeah, Jerome, go ahead.
But do you deal with different permittivities? You know, it like in other words, different materials, or is it just all the one material?
No, you can have as many materials as you like with different dielectric constants and loss tangents. And I haven't run an example yet, but it should also support different permeabilities, but it's not really intending to target rotating machines or anything like that. So the I haven't checked that, but it's inherently there, but there's probably some mistake there. But other than that, any dielectric configuration you want in a 3D space.
Okay, I do have a comment. When you talk about the surface integral that is missing from
Yes.
FEM, so this is really N cross E tested with some other H curl variable. So it's N cross curl E, right? Tested with V, whatever, on the boundary.
Yeah, I'm trying to go back to that. This one, right?
Yeah, it's N cross curl E tested with W on the boundary.
Right.
Or
yeah.
part of the boundary. Okay, so there is one. I don't know what version you're using. There is. We have this tangent trace integrator. It's there in the new master. If it's not exactly what you need, it's probably very close.
Okay.
Maybe you want to take a look because I used something. I needed some similar term.
Okay.
If it's not the same, really.
Yeah, I'll check into it. There was a support thread that I filed 6 or 8 months ago. I don't know exactly where this was discussed, and that's where I posted,
Okay.
I need to support this. How do I do it? And the answer came back, no, because of the need for the normal component on the surface.
Right.
Yeah, it's just inherently not supported.
But yeah, that's right.
Yeah, I'll trace down the tangent trace integrator and see if I can make some progress with that.
Okay, and the other question I have is, maybe I missed that. Maybe you said so. Now, are you using any kind of absorbing boundary conditions that you want to replace to? Okay.
No, I haven't put that in yet.
Okay. We also have an example with simple, really, PML.
Right.
Yeah.
Yeah, I would definitely be going in and looking at that and seeing how much of it
I mean,
can
it's a
copy.
simple example. It's a simple scattering, in a box.
Yeah. Really, where I am at this point was to get something running up to what I would consider kind of minimal commercial quality, which is get something that runs very well with regression suite backing it up and a lot of examples. So as an example, for the last week, I've been running the regression suite in a loop. It takes an hour and a half to run the 3D regression suite, and I just set it up to run it 40 times and just looking for anything that would pop up. And actually, something does pop. Well, it used to pop up. I fixed it now, but the preconditioner in PETSI fails like 0.8% of the time. And
so I was going to ask about that. What is a solver in PETSI?
it's just
an indefinite system.
Yeah, GMRes.
It's GMRes with
with
what preconditioner?
Koleski, and it.
I complete, but
just
but this is not. This is indefinite, right? This is indefinite system. So
it's at times borderline, I think, for the preconditioner, because it fails like 0.8% of the time. But what I find is that if it fails, just try it again, and it works the second time. So
okay, that's not very reassuring, but okay.
Okay. Basically, I tried every preconditioner that PETSI supports, and Koleski is best. LU is second best, about 10% slower. But they both run pretty effectively, but occasionally, rarely fail. And so I'm just catching that.
How big are these systems? How big are they? Because if it's not, if they are not that big, a direct solver will handle this, and you.
I go up to, I go up to a couple of million DOFs.
Oh, okay.
Is that considered small or large?
It depends. On a laptop, it will be large.
Yeah, no, I'm running
on a big machine. Yeah.
Dual processor, a dual slot, dual CPU Xeon machine.
Yeah, this would be considered large, I would say.
Okay.
On a large machine, the direct solver will handle this. I mean the preconditioner is it's a open research problem for those for electromagnetic or time harmonic electromagnetics. So
well, what I find is, unless the preconditioner fails, in which case I just rerun it, and then it runs. It converges.
Some magic behind
2 iterations, 3 iterations.
Okay.
I mean, it just bangs it out. It's just quite stunning. In fact, before I got to the preconditioner running well, a long time ago, it'd take 5,000 iterations to solve on a small problem. And then I finally got the preconditioner set up right, and I thought I'd forgotten to solve the problem that I'd commented out to solve, because it just banged it out so quickly. I just almost didn't even see it. It's like, what happened?
Okay.
Now, being an engineer and not a numerical scientist or anything, I come at things very practically. If it works, test it to death, and then beat it to death, and then move on. If it's not supposed to work and it's working for me, then I really wouldn't know that.
See.
I would suspect that if you increase the operating frequency that you're at, you're going to run into issues with less speed.
Right? Of course. Yeah, of course. I mean,
you're probably just by nature getting lucky. In this case.
Okay.
Yes, exactly. Yeah, exactly.
You need to go to LU.
It will be more indefinite. It will be,
Yeah, high frequency depends on the dimensions of the problem, and so in the problems I've run them at the frequency range is appropriate for that problem, and so far I haven't seen it issues. But yeah, if I took one of my, well, calculating S parameters, you're bringing in the single mode operation anyway, primarily, and so just in any engineering type application, you're just not going to push it to a high frequency that's not appropriate for the structure that you're actually trying to test. So that may be why I haven't seen it. It's just because I'm using frequencies for which the problem is designed.
Yeah, makes sense. Can I ask a question about? I guess it's actually on this slide. Is it in a single simulation? Can you calculate S parameters into multiple modes on a port? So say I have like a symmetric and an anti-symmetric mode. That would be like 2 boundary conditions on the same surface. Like, can you calculate both of those modes in OpenPAR-EM 2D? Can you then calculate like S1, S21 and S31 into both of those modes, or is that not possible? Like how does that work?
Yeah, that is definitely going to be in there. It's supported right now. I just haven't tested it to see what problems I need to fix. But OpenPAR-EM 2D can calculate arbitrary numbers of ports. So you can get, like if you have a two-conductor transmission line, you can get the even and the odd modes. And then, the S parameters don't really care what port you're on. It's just, it'll import from OpenPAR-EM 2D the port setups. So strictly speaking, I don't see a limitation with doing multi-mode at the ports. That was always the intention of supporting that. I just have not built up those examples yet to solve it, and then work out whatever issues I have. But that's always been the intention to support that.
Yeah, I guess not coming from as much of an electromagnetics background, it's always confused me because if you, I guess, look at it here, it's almost like your gamma. So if you on the like the lower left here, you have this N cross del cross E is equal essentially gamma ET. And so then what your boundary condition ends up looking like, it's like gamma 1 plus gamma 2, right? So it's like, does that physically make sense? Is that actually what happens?
I think right now what I think will happen is you can only pick one gamma. And so if the gamma for the two ports is radically different, I think that will introduce an error. For the engineering
I see. Okay.
Yeah. But I think for the engineering,
you get the same 3D solution essentially, but then you calculate scattering parameters into each of the modes, and the 3D solution is the same. It doesn't really care because the damping on the other side is the same.
Yeah.
That makes sense. Yeah.
So that's in effect implementing the first order absorbing boundary condition.
Right.
So when you use gamma for one mode, say the odd mode, you'll be matched then. But for the even mode, the gamma will be slightly different. So you'll be slightly mismatched for the even mode. And so that will distort the solution slightly.
Right.
So I don't know how much all that will affect practical applications. All I can really do is just start building up good examples and seeing how it goes, and then maybe I'll figure out a clever trick to get around that. But that's sort of what I'm expecting right now. But in the real world applications I'm familiar with, the even and the odd mode gammas aren't really very much different. So, and you're primarily interested in say the odd mode. So if the even mode's a little bit off, you really don't care that much, I don't think. So I'll have, it's only, I'll find out when I start working my way through those.
Yeah, that makes sense. Yeah, if no one else has anything, I wanted to maybe draw your attention. So there's a ton of overlap here with a project that I work on called Palace. You mentioned that there's maybe a lack of open source solutions for computational electromagnetics, and that's kind of, we had the same ideas.
That's the AWS one?
Yeah.
Yeah, we got started at the exact same time.
Right.
We looked around and said, there's nothing we need, so I'll go do it. And then not knowing each other's efforts, we've been kind of doing the same thing.
Yeah. So we come much more from a solver's background and a computational background, I'd say, than an actual traditional computational electromagnetics or just straightforward electromagnetics or E backgrounds. Like both of us have mechanics and fluids backgrounds. But so we're much more focused on that, but the use case is very much the same. So we do all of this stuff and at scale. Mm-hmm. And it might be something to check out or combine. Like we'd love to have your expertise. Mm-hmm. It could be pretty fun, and we could build some pretty cool stuff. So like we do, like we call them waveports, numeric waveports, but like solving 2D eigenvalue problems and driving mm-hmm. solutions, calculating S parameters, all that stuff. And then we have adaptive fast frequency sweeps also to like speed up the whole process better.
My thoughts are on
if you want to reach out, please do.
Sure. Yeah. I thought it never hurts to have two people trying it, but I think you guys are targeting extremely large applications with using cloud infrastructure. And I'm thinking that my target audience is just an engineer with a computer at home who wants to play with some ideas, that maybe wants to start a startup, maybe wants to just educate. And so I'm kind of intentionally not running cloud stuff or GPUs, because my target audience is a guy with just a regular home PC. And so I'm kind of trying to optimize for that use case.
While true, like we certainly do target large applications. I guess maybe one of the driving principles behind both FEM and also our code is that it can be single source and do both.
Yeah.
So I run a ton of stuff on my laptop. Like I can solve a 5 to 10 million degree of freedom eigenvalue problem on my laptop on like a MacBook in 30 seconds. It's kind of absurd. Like, so the performance benefits that you get from cloud scalability and all of the like memory bandwidth improvements that you get also lead to being able to run on lighter hardware in our experience. And so while yes, we do target large hardware, there's nothing cloud native about it. It is a C++ code that you download and build. And you can build it on your Xeon machine and run it on as many cores as you want, whether you have a GPU or not. So it very much so it applies to both scenarios.
Okay.
Okay. Next thing, Brian, one more time. Thank you, Brian. It was a very nice talk.
Yeah, thank you for the invitation.
And I think Aaron will be in contact with you. Maybe if you can share your slides.
Okay, yeah, sure.